Hello. So I've been spending a lot of time thinking about how should you design a robot if you want to make it easier to actually learn the control policy, especially if you want to do it directly on hardware. And one of the big challenges with this is that if you run into a failure, this can be really costly, but also really uninformative for your gradient. So robustness is something that's really key. And a good tool to quantify this is something called viability theory. So let's start with that. So the viability kernel in state space is simply the set of all states for which there exists at least one control input that will keep you inside the set. So the other way to think about this is that once you've left the set, you can never get back in no matter what control input you apply. So this red trajectory cannot exist, and by definition. So when you design your control policy, what you're trying to do is you want to make a region of attraction as big as possible. But by definition, this region of attraction has to live inside your viability kernel. So when you design your system, you want to do one of two things. You want to either make your viability kernel as large as possible. What I'm going to argue today is that what's perhaps more important is you want to give it some sort of structure that makes everything more robust. And to find this structure, we need to look at viable sets, not just in the state space, but in the state action space. So I'm going to illustrate this with a very simple example. Our toy model is just going to be the spring-loaded inverted pendulum. We're going to have a one-dimensional state space. So every time we're at apex, we're going to just look at the normalized height, so potential over total energy. And we're going to have a one-dimensional action space, which is just the landing angle of attack. You get to choose this again every time we're at apex. So we can brute force compute all the pairs of state and action, and this is what we get. And the way you read this is that if you're at some state, for example, up here, you get to choose from any of these actions. And if you pick something here in the bluey-green region, you will end up going down in your state space at the next apex. If you pick something in the swarm region, you will go up at the next apex. And if you pick a state action in the gray region, these are all state action pairs that will transition to failure, which in this case is just defined as the body hits the ground or your reverse direction. Now, if you take this colored set and take its projection in the state space, this is your viability kernel. No matter where you are here, if you're very low, you can take something that will take you back up. If you're very high, you can take something that will take you down. And you can always stay inside this set. And your policy has to live inside this set. So this is saying the same thing in math. Basically, a policy is a viable policy if for any state in here, the policy maps the state to an action inside the set. And this is a really general condition, right? In fact, your policy could even just be completely stochastic and randomly sample actions from inside the set, in which case you'll never converge to anything, but you'll also never fail. And since this is really general, we can start to compare different systems, different designs, before designing the controller. So for example, this is just another slit model, but with a nonlinear spring in the leg. And this is the viable set in state action space. And if we look at the viability kernel in state space, this is exactly the same. We just look in state space, we won't see any difference, right? But we have a lot more flexibility, a lot more space to actually design our controller here. And this is also where we get our robustness. So if you start to inject noise into the action space, this is going to basically shrink the set where the controller has to live, because you have to be a bit more conservative to account for the noise actually potentially pushing you out into the failure set. And because this is a lot slimmer in the action dimension, if we start to add more and more noise, this shrinks a lot more quickly, till eventually it becomes an empty set. And putting noise into the action space is also how we do exploration. So basically, you get to explore much more aggressively with this system. Now, everything I've shown you so far has been relying on brute force, but it turns out we can do use this setup to actually do model-free safe learning. And I don't have the time to really go into the details, but the key idea is we're going to take a measure of the set. So in this case, it's just taking a histogram, basically, and for every point in the state space. And we can map this back into the state action space by sampling the dynamics. So if we're at this point and we sample this action, we look at where we're going to go. We take that measure and map it back into here. And this is what we get. And since this is sample-based, you can hit this with your favorite machine learning tool. So for example, here we're using Gaussian processes to safely sample the state action space and learn both the C measure and the set of viable states at the same time. And that's it. I'll happy to take any questions.
after you add the Gaussian process into the pipeline, how does the computational complexity scale up with the degree of freedom of the system?
We haven't checked that yet.
Repeat the question.
How does dimensionality affect things once you use Gaussian processes instead of brute force? Yeah. So we haven't tested that yet, but I would expect just from typical things with Gaussian processes, should be able to get to maybe 8 or 10 dimensions.
Right there?
Yep.
So what is the Gaussian process fitting?
Right. So the question is, what are we fitting with the Gaussian process? Basically this, and this is basically for every point in state action space, what is the robustness of the state you will reach after you're sampling the state action pair? Yeah, sort of. So basically, if you pick this point, you will reach here, and this measure is basically how many actions you have available, which is kind of how robust you can be. So how much noise, you can think of it as how much noise you can afford, or how not precise you can be at the state that you reach from there. Yeah. Okay.
I have a question, which is, let's say you're in the viability kernel, but you're not in the reachable region.
Okay.
Okay, so you're on the outer perimeter there. Under what circumstances, I'm assuming that we would still like to get into the reachable region.
Mm-hmm.
Under what circumstances can that happen?
Oh, okay. So maybe to clarify a little bit, it's very rare to be in the viability kernel and not be in the reachable region, but I guess that can only that happens only in cases where you're. This is kind of tricky to illustrate. Basically, if you're lucky and you get a perturbation that pushes you back in to the reachable region, that's pretty much it. Okay. And if that was confusing, talk to me after, and I can go through it. It's simple, but it's hard to visualize.